And I never use Microsoft products, or hardly use Microsoft products, except for PowerPoint. I had to install, I had to register as an education with the OVGU to install, to log in. Okay, sorry for that delay.
No, no problem.
I'll just here try to get
So for us, we don't have option with Microsoft Teams. This is the reason why we're using such a complicated system. But yeah, I like it also.
No, it's good. Okay, so so should I start? What is the?
Maybe I can just present you a little bit.
Please.
So very happy to welcome you, Claus-Dieter, and you are professor at the Institute of Physics at Otto von Guericke. Sorry for the pronunciation. Otto von Guericke Université de Magdeburg en Allemagne. So you're going to talk about cavitation and soft matter. So go ahead, the floor is yours. Thank you.
Thank you very much. I'm very happy actually for this invitation, because I would like really to make some more contacts with you guys. Claude was in Sarah. He gave a presentation in our seminar last semester, I think, and we have been working now a lot with soft matter, but not really a lot of experience. And I see you have lots of experience, which we want to tap on. We're coming in this field from the liquids towards the solids in the group, and I hope I can show you something what we have been doing. It's a lot of them are actually not published; they're just in the middle of the make. But I think that's also the nice thing to share this kind of more or less fresh out of the lab work. We are. Have been working here. I think Julian is here. He helped me with the link. That is, he did his PhD. I say now Singapore, but he did part of the PhD here in Magdeburg the last year. And I will present a lot of his work, mostly his work, and follow up. Also, Petro, he was very important in some of the understanding what we have seen in the experiments. Petro Quintosu is a professor at UNAM. We have now some connection with Daniel Fuster. Probably you know him. He's working on multiphase flows at UMPC as at very good groups there in Paris, doing numerical simulations. Here in Germany, we have a number of people working on it. I'll show you. I'll just name here the names. They're postdocs and PhD students working on different aspects. Now, this is the group in Corona times. So that the good news is the lab is open. We can do experiments. The students can't come to the university. And by the way, if you have any questions, please stop me. Or even if my sound or microphone is not so good, please stop me anytime. Okay, so this is the group. We keep distance from each other, but we still work in the labs. Good news. And the menu, I'll try to limit to make it go fast through it, so it's more time for questions and comments. I would like to talk a little bit on single bubble dynamics in elastic solids. So we try to understand what is the effect of the solid, which has a restoring force and which allows for waves traveling in the solid, which are not only longitudinal but also transversal waves. So shear fields and stress fields and also displacements is something what we are interested in. Eventually, if we want to go for an application, one needs to do look through it, not by optical means, which is our expertise, but by acoustic imaging, and we are working a bit on this field too. There's a PhD working on acoustic imaging of shear waves.
Ouais. Ah d'accord. Ok, ça va. D'accord. Essaye de trouver quelqu'un. Ouais, ça roule. En tout cas, c'est très gentil de. Ah, ça, désolé, je t'ennuie à chaque fois avec ça.
Ah, Maxime, on t'entend. Tu peux couper ton micro? Thank you.
Okay, sorry, my French is very lousy, so I can't comment on that. then we are looking on shockwave bubble interactions in elastic solids and propagation of shockwaves in bubbly elastic solids, similar to that what has been studied in bubbly liquids. And at the end, I want to show some very exciting results. This is a bit has been matured because we've published this already, but we're still working on it and show you the latest exciting results that you can actually create very strong cavitation if you have elastic walls. Okay, let's go through it. The first part is about stress and strain fields in an elastic solid generated by a single bubble, and we are using laser-induced bubbles. I just show you that it is possible to describe a Rayleigh bubble. So if you are familiar with the Rayleigh-Placid equation or the Keller-Mixes equation, what you have additionally, can I add can you see my mouse cursor here? Yeah?
Yes, perfect.
Yes, okay, yes, okay. So there are this is the standard Rayleigh-Placid equation, and if you want to describe a bubble dynamics in an elastic solid, you can do it, or at least in the group of Eric Johnson he presents additional pressure terms which come into that for the bubble when it is in the static situation. When it is at rest, you have a pre-stress of your solid, and you have a pressure term when the bubble is moving. Here this E, this is the elastic pressure description, and these two can be described by different materials. You can do that with a linear elastic material, or there has been work by Young and Church coming from this microbubbles, shelled microbubbles approach, or these neo-Hookean, which has some non-linearities, and they describe somehow how is the stress in the solid and how that actually affects the forces on the surface of this bubble. We have done some experiment simulations and see that most of the time, actually, even a Newtonian liquid is not so bad to describe bubble dynamics. So this is a bubble which is expanded a little bit and then it oscillates. And you can use different models and compare the behavior of this bubble. So this is just work in progress. You can use a simple Keller-Mixes type equations to describe bubble dynamics to some accuracy in liquids. But we are actually more interested in what happens if these bubbles are not spherically oscillating and things are getting a bit more interesting. We use gelatine here in all the experiments. And the Young's modulus is adjustable between a few kilopascals to maybe something like 20 kilopascals by changing the percentage of weight percentage of gelatine into the water and then cooking it. So this is an example which we are working on, looking at the strain fields. We put in particles into the gelatine, and then we create a bubble. And that is here a bubble which is expanded, and then it collapses. You see quickly a shock wave emitted by it. And if you look carefully, these particles, they actually move. When I start this movie again, you see a little bit the particles moving out, and then they're going in. And so we can actually, by following these particles, we can follow the strain in the solid. Now, if you do that with a simulation, you can just do the same. And this is just a Newtonian fluid, and we are doing open foam simulation. This only allows also to do some non-spherical bubble oscillation, and one can compare things with experiments and simulations and understand what are actually these shear stresses from the simulations. We started everything on looking at stress fields in the PhD of Julian Rapid, and we have been working here also together with Yoshi Tagawa. He's at Tokyo University of Agriculture, and have looked at the stress fields. And this is an early picture taken with a linear polariscope of a bubble in gelatine. So how do we take that picture? So I go quickly through it. I think you know that if a liquid can also be birefringent, but solids can become birefringent if you put a stress on them. Gelatine is a nice material. That's why we did our experiments with gelatine. It becomes birefringent with a strong constant. Here it is C constant. And so it becomes an oriented material. And if you put in light of arbitrary polarization on different polarization, then depending on your polarization, you will have two different beams, the ordinary and the extraordinary ray, and both have different index of refraction. So they move at a different velocity. So therefore they become retarded. Now, if you combine the two together, you end up with an interference, or with a phase difference between the two, and you can look for fringes in your pictures which are showing destructive or constructive interference. Therefore, we can look at the stress fields or the orientation of the material by looking at these fringes. A particular technique is called the circular polariscope, that has the advantage that it doesn't really depend on the orientation of the polarizers and analyzers on the stress field. So if you take linear polarizer and analyzer and polarizer without quarter wave plates, which are these two objects here and here, if you don't put them in, then you also get a possibility that you get no light because the polarizer is just in the orientation of the stresses, and you don't want to know that. You want to know how it's deformed. This helps here because it creates a circular polarized light, and then you can analyze actually your phase difference here via the intensity. This is very quick. This is a standard procedure. It can also become quantitative, but we have not done very much in this direction. How to do that in the experiment is rather simple. You shoot a bubble here, which we always do with lasers. That's our standard way of creating bubbles. We pulse a laser in and focus it into a gelatine. So the energies are in range of millijoules, and for a few nanoseconds, and then we use a continuous wave laser. We have a polarizer, have an analyzer, and then here's lambda quarter plates. So we use actually monochromatic light to see only a single wavelength. And the bubble is generated in the bulk and then put in a high-speed camera to look at the bubble dynamics without the polariscope. This is a movie. Bubble expanding, collapsing. Actually, look at this picture, you would not really know if this is water or solid or liquid. The bubble, it becomes a bit bigger. There is, when you create a bubble in gelatine as compared to water, a bit of non-condensable gas is generated, a bit more than just in pure water, because of all the carbon in the gelatine. Therefore, the bubble doesn't collapse as strongly as you would expect in water. But basically, it's the same. Now, if you create that with a polariscope, you see a bright field around the bubble, and that is where the gelatine is actually stressed, and that goes away once the bubble has collapsed. One can then look at the bubble dynamics, and there's also displacement of the center. This is showed here in the two graphs. Bubble expands, collapses, and then you see there's a motion here going on because the bubble is not perfectly spherical. There's a little bit of non-sphericity, which is coming from laser focus. Is maybe sometimes not perfect, or it's actually never perfect. So what you also can do is you create a not so nice bubble, a little bit. Maybe sometimes you create two bubbles at the laser focus. Here's an example. It was not really perfectly spherical in the beginning, and therefore it moves when it collapses. Moves back and forth, surface oscillation going on. And if you look at the stress field, it looks similar like the beginning. And then if you look carefully now, you see that there is the stress fields, there are multiple stress fields now generated, and these are actually waves which are leaving the bubble from the center. So the bubble, when it collapses non-spherical, it creates stress waves in the solid, and these are easily visible in this gelatine, this transparent gelatine, using this circular polariscope. If I say easy, maybe somebody is saying, oh, it took me about a year to set it up. Indeed, it isn't. It was not trivial. But once it is set up, it looks very fine, and you can nicely see wave emitted. So in summary, you can see nicely bubbles, the stress fields generated by bubbles, and start looking into how they appear. To control this non-spherical collapse, we looked into the bubble dynamics near a surface. This has some medical application. There's a lot of work done on getting rid of your tattoos. So you shoot with a laser on your skin. What you eventually do is that the laser focuses in the tissue and destroys the particles, but you might also create cavitation bubbles. So nearby a free surface, you can also do some ablation of the tissue or the skin. Many other applications. So what we do is we just do the same experiment, but now we have a free surface. Here you see that bubble is really created very close to the free surface and in a cuvette. The free surface here on the top black, and then we look at the dynamics. We don't see here now the bubble, but we only see the stress fields, and you see a very bright region in the center, which was not before. When a bubble collapses spherical, you get a bright region which remains there, and you get also black regions on the side, and they leave the field which has been generated. So you see some black here on the left and right side. This leaves the whole thing. Consider this is an axisymmetric, mostly axisymmetric experiment. So what you see is now a wave traveling like a cylindrical from the axis of symmetry. The bubble itself moves downwards, and when it moves downwards, it creates a lot of stress here in the center, stressing it, and it even leads to a rupture of the upper part. So you create a small, crack-like intention on the top. So the free interface, the gelatine interface, forms this very sharp-cornered interface. Can you all? Are you already still with me? Okay.
Yes, we are.
Good. So this is some experiments we have been working on this. You can do some simulations, but really this was a solid state simulation, no fluid mechanics inside. We just applied a force which moves downwards with some constant velocity, and then we look what kind of stress field is generated if you move this downwards with a free surface here. And you see something very similar. So this bubble this is putting artificially. So this is more like a demonstrate where the bubble is there, and when it moves downwards, because of this free surface, the bubble moves downwards, it creates this stressed region, and then the stressed region travels outwards as a cylindrical wave, stress wave, and we see that nicely in the experiment too. One can also look at the surface, and just to show that we have been doing it, in the publication is a bit more stated on that. You create surface waves when you create a bubble near the surface, and in the center you get this the force leads then to this crack-like this pointed shape here, and that is there for some time while the bubble is here on the bottom visible. Okay. We can do the same thing in looking at the strain fields, how the solid is displaced. Here, again, particles are inside. Sometimes you catch a hair, and the bubble expands, and it collapses, and you can again follow here the particles. We haven't really analyzed these movies, but there's a lot of things are going on. And if you look with suitable illumination, and that is a very short laser pulse, that's what we are using in the labs. We illuminate these high-speed movies with something like sub-picosecond laser pulses, which are coming synchronously with the frame of each pictures. You can see beautiful shockwave emissions. And here, this is the bubble, which from one frame to the second, here from left to this frame, within oh, I don't know, is it 2 microseconds, 500 nanosecond or 1 microsecond, it collapses and creates this this toroidal bubble. This is the bubble, and all the other stuff is shock waves emitted. It's a very complex sequence of shock waves. The elastic solid helps here a little bit to see nicer these shock waves, because the bubble collapse is somehow not disturbed by. It's more, the viscosity helps to keep the shape of the bubble more homogeneous or more axisymmetric. One reason why you create the shock wave is because you get a jet from the top hitting the lower boundary that creates a shock front, and then you create here these toroids, and this torus even collapses, and you get overlapping waves, which might lead to some other local cavitation. The summary is here for this kind of research was that the aspherical collapse can generate shear waves, and we can control that very nicely near a free surface. It becomes a repeatable thing, and you create shear waves. And we are looking into how to look at this, how to measure these shear waves, a little bit without the optics. The optics is fine, but then you need a transparent material. If you want to look for like in a medical application where you create cavitation in the body, maybe by thermal ablation or by shockwave histotripsy or other HIFU techniques, you might use these bubble collapses to look at the shear wave velocity, and then measure out of the shear wave velocity the properties of the tissue if it has changed. Here's a simple experiment where we're starting with it. This is plane wave imaging. You probably know much more than I know about plane wave imaging. We are looking at rising bubbles. So we can do plane wave imaging of a single wave, or here is a bubble. Here are bubbles rising in liquid, no solid. They're moving upwards. And this is the picture with a transducer taken, recorded. And here a single plane wave is used. You can use multiple plane waves, therefore the frame rate goes down. And here we use 21 plane waves, which are compounded. That reduces the frame rate from 40,000 to 2,000 frames per second. And you see that the picture is actually better. But for just to look that these are bubbles and how fast they move, you don't really need that. So the good news is here you can do plane wave imaging nicely with cavitation bubbles, or with static bubbles, just because the impedance difference is so high between the bubble and the liquid or the tissue. Therefore we can be extremely fast and look if this is really possible to look for cavitation bubble dynamics with an ultrasound device. So the experiment was the following: create a bubble with a laser, again in gelatine. We look with a camera and then the light source. This is the experiment. On top is the transducer. So the laser comes from the right, shoots into that gelatine. On the top is a small acoustic window. This one is a Verisonics device, so you can really look at the radio frequency data, and then we look for through this coupling jail what we can see. Here is a comparison of what we see with a camera, and this is the bubble dynamics. The bubble is generated here, expands, collapses, a few bubbles collapses. These are just the data points recorded. The bubble was not very spherical. And then we have put over it what is the calculated radius time from the acoustic images recorded with the Verisonics and plane wave imaging without compounding, just a single plane wave. And we get pretty good agreement between the measured bubble dynamics and the acoustic images. Important to note is that in the beginning, we create some shock waves by the bubble, which expands by the laser breakdown, and that leads to a lot of ringing, and also the transducer become a bit blind. So we haven't solved that problem yet. Later on, we can get rid of these ringing by using a frequency filter, and therefore we can get rid of all the noise and reflections and only see that what is coming from the transducer. Also, the transducer is running at 5 megahertz, which is not ideal actually for resolving this kind of bubble radius of sub-millimeters. It would be better to use a higher frequency. However, we are pretty happy. We can record bubble dynamics with a Verisonics device with more than 40,000 frames per second. So this is really a way to look at bubbles, cavitation bubble dynamics, and also the shear waves generated by it. Are there questions to it for this technique? If not, I continue. I'm running a bit.
I
yes.
have a question.
Please.
Can you, on your optic image of the bubble, can you just mention the dimension of the image that we are looking at?
Right.
If you come back.
Yes. So yes, they're always about the same size here. Yeah. Here, this is 500 microns. Here, they're typically about 1 millimeter, 2 millimeters in size. Yes, the bubbles are typically 1 millimeter in diameter.
All right. Thank you.
We are always in that range. The reason why the size is there is because we use nanosecond laser pulses, and they generate this kind of bubbles. If you use shorter laser pulses, you get smaller bubbles, but then you have the problems at looking at it. It becomes more difficult and faster. What we are also looking at shockwave propagation in bubbly soft matter compared to bubbly liquids. So if you apply shockwaves, you have a tension part and you create small bubbles. You apply a second shockwave, and the shockwave interacts with this first bubble generated. This is more important in elastic solids. In elastic solids, the bubbles, they remain there for a long, long time. Or sometimes the tissue or the gelatin we're using is super saturated with gas, so they actually grow in time. So you don't get rid of by buoyancy of the bubbles, but they remain there. So the second pressure wave interacts with these bubbles. And we realize that how important that is by these experiments, which I'm going to present you. Creating bubbles with a shockwave lithotripter, which is used for kidney stones, but adapted for labs. And we look with a high-speed camera. This is the samples we are using. We have been working a bit harder to get good samples in a reproducible way. So the trick we are now doing is we use a commercial plastic, which is sufficiently transparent for the light. On the front side, we put a glass plate, and on the bottom, we have a cover, but which is detachable. So the bottom there is a direct contact of the gelatine here with a water bath. So this is submerged in water. And then the rest is the gelatine. And here front, we have a clean glass plate to image the bubbles. On the back side, it is not so nice, but we are only putting the light through that. This is one example. And after you placing some shots with a lithotripter into that gelatin, you see the bubbles, and they're pretty big here already. They're not initially so big, but they're big because we wait some time. So over time, they actually expand to rather large size. Reason again is there is a lot of gas in the gelatin, and that diffuses into these bubbles, and they expand. This is an example of what happens if you put a pressure wave through your gelatin. Here, this is the shockwave profile. It's not so high, it's maybe 14 megapascals. And the tension here on the backside is also not very strong. It's maybe 1 to 2 megapascals. So it is not that strong, but it's sufficient to generate cavitation bubbles. So you see here the wave traveling through it, and you create bubbles. The bubbles expand, and let's watch this movie fully. The bubbles expand pretty large, like cavitation bubbles. A lot of bubble interaction is going on, and then they shrink again slowly. The movie hasn't captured it, so it depends on how fast you record. This kind of cameras, they can't record for very long, but you get full frames, even up to 1 million frames per second. Now, this is what you see. The bubbles are not there when the pressure wave travels through it. You see the front of the tension is here, and there's a top. And out of this, you can estimate what is the speed of sound here, which is approximately what you expect for gelatine is about 15 to 1600 meters per second. Now, the second shock, you have created bubbles, waited some time. So these bubbles are the remainers. They don't rise anymore. So these bubbles are interacting now with a second shock. And you see There's a bit of jetting of these bubbles happening, and the bubble expand again, but it seems not expanding as strong as in the first time. And here you see the bubbles, and you can see the wave traveling through it, but not now the tension, but the pressure wave it compresses the bubbles. So initially the bubbles are compressed here, then they're here, and then they're here. So you don't do it for 1 or 2 times, but you do it multiple times. This is an example for 8 times. You have 8 times the shock passing through the same volume. You wait about 10 minutes between shocks. And now the wave travels through it. And we see that the bubbles collapse again. And we were really astonished what we actually see. On the right side, I can show you a little bit of a measurement. This is the pressure measurements. This is put. Yes.
Klaus, can you hear me?
Yes.
Yeah. We had a problem with the slides. Can you go back to the previous slides? When you were talking, we could not see the image at the same time.
Okay.
So sorry for that. Can you say that again? I think 2. Which is the one before? Maybe one more. Yes, we have not seen this one neither. Yeah, so maybe.
Okay, so stop me immediately if you don't see something. So this is the pressure wave traveling through a gelatine, which is virgin. There's nothing happened to it. It is just coming out of the fridge, has reached room temperature. Bubbles expand to pretty large sizes. Yeah, there's and then they shrink. You see the shrinkage happening around now. Okay. Okay, let me see. Here the bubbles are shrinking. Okay, this is the pressure wave, about 140 bars. Positive pressure, 10 bars. Negative pressure. Not a very steep shock wave. Yeah. This is the wave when it travels through it. Front, you see through by the tension. So you don't see the pressure wave, but you see the tension. The tension is here. At frame, after 1 microsecond, after 2 microseconds, you see the bubbles here on the top. And out of this, you can estimate a velocity, which is very much the velocity you would expect, is about 15 to 1600 meters per second in that sample. The frame size is, I'm not pretty sure, maybe something like 8 millimeters or so. Again, so this is also less than a centimeter, I think, on the width. First wave we have seen. Now the second wave, you have already bubbles in the gelatine, and the wave travels over these bubbles which are already present in the gelatine. Can you see that? Yeah,
yes.
So the bubbles, though, they shrink because of the pressure wave traveling through the gelatine. Here you see also there are the bubble collapsed, then they're collapsed in that height, and then they're collapsed in that height. So more or less on that size, also the wave is focused. It is more or less a planar wave. We will see the wave later, a bit more clear. And now if you do it as 8th time, so 8 shock waves, the 8th shock wave is traveling with a lot of bubbles present in the gelatine. Oh, sorry. And here you see again the bubble getting compressed from below, and then this compression wave travels through the field of view. And we were very excited by this observation. Here on the right side, you see the pressure. This gives you already an indication. So the pressure is now plotted logarithmic. And the recording, we can do better, but you see that the amplitude after the first is the second shock, the third shock, the fourth shock, the fifth shock, the amplitude drops drastically. So the pressure wave is much, much weaker when it travels. But the more exciting thing is that the pressure comes later. So after the first shock, you have at this time, you get the amplitude. After the second shock, you get this time, and third shock. And it's considerably. So it's about 15 microseconds later than expected, than you would expect it, or that would you get without presence of bubbles. So you can look, what is the speed of sound in that bubbly elastic solid, and you get a strong reduction of the speed of sound. here the preliminary results are that we look for the void fraction, but this is a 2D void fraction. So don't take it as a percentage in 3D. It's much, much smaller. It's less than 1% from the void fraction in 3D, but in 2D, it would be about 35% of the volume is occupied here at the end with bubbles. That means the projected void fraction of all the bubbles in that field of view. And the shock pressure, shock wave velocity drops from 1600 meters per second, that is for gelatine, the expected value, down to less than or around just 300 meters per second. So it's a drastic reduction of the speed of sound due to the presence of the bubble. And we were puzzled by it because bubbly liquid, they do show something like that, but then these are linear waves, and the wave was expected to be actually not affected directly by the presence of the bubbles. So we spoke with Daniel Fuster about that problem, and he ran his fantastic simulations. He simulated the whole thing, full Navier-Stokes with compressible bubbles. And what he sees is that he gets the original wave, that is the pressure wave, which goes through the elastic solid. This is in the vertical axis is the position, yeah, and on the horizontal axis is the time. And now what he plots is the local void fraction, or the size of the bubbles, as initially the size of the bubble is constant, and when the wave comes, the bubbles are compressed and then it re-expands. So this is a bubble at that position, it compresses and goes up. And now the first bubble compresses here and the last bubble compresses here, and this gives us a velocity with which these waves travel through this bubbly solid. And then we look at this, and this is the speed of sound you would expect. This is the wave, the initial wave which travels through the solid. But later on, this is you see the shrinkage of the bubbles. This initial shrinkage is small, but the second shrinkage, which is much stronger, and that is moving at a much lower velocity. Here you see that is maybe something like half the velocity, something like maybe 1,000 meters per second. But if you add more and more bubbles to it, you can reduce that velocity down to somehow this velocity which we have observed down to something like 300-400 meters per second. And this is a coupling of the bubbles, so that the initial wave is dampened, strongly dampened. It doesn't lead to a strong collapse of the bubbles. You see that? Initially on the bottom, yes, these bubbles are collapsed. On the top, they're not feeling it. They're only collapsed by the neighboring, feeling the neighboring bubbles.
Are you still at slide 41?
Yes.
Okay. I had to do. Okay, please continue. It's good.
Yeah. So what we observe is that the pressure wave, this wave which we see, is actually coming from the bubbles, from the oscillation of the bubbles, transporting the energy from the hitting shock wave. The shock wave thus only affects the first bubbles. The later bubbles are not affected by the shock wave. It is more or less completely damped, and we get dynamics only from a propagating wave of bubble oscillations. So therefore, we wanted to look a bit more careful by placing the bubbles at positions in the solid, and we do that by laser. So we again have an elastic solid. We create with a laser bubbles at certain positions, and then we look how these bubbles collapse, and our particular illumination, which sub-picosecond illumination, can give us nicely these bubbles, and we apply a shock wave here from below with a little tripter again. Yeah. Having this availability, so we can now generate bubbles at precise locations. Here, for example, these are bubbles along a horizontal line. The shock wave comes from below, and then you can play this game. You can expand these bubbles, and these bubbles expand large. You also get some bubbles from other places in the gelatine, some nucleation. But you see here nicely how these bubbles transport the energy from the left to the right. It's like a cascade of bubbles, creating now a wave from left to the right. And this should just show you that this is work in progress. We now have the ability to create bubbles at certain locations and look the interaction with waves with these kind of bubbles. This was just for fun. I asked Fabian Reuter, to a colleague here, to make a dodecahedronic cluster. That means a platonic solid at the corners of this one, and you can make bubbles at these positions. And this is, you see nicely, generate them with a laser and a 3D position stage and some clever algorithms, and then you can create bubbles at arbitrary position in the gelatine. And then after waiting some time, you see the bubbles, they have expanded. That was probably a bit too long. Therefore, the bubbles here left and right are the same, but they are bigger. And then we apply a shock wave, and not so much is happening because the bubbles are a bit too big. But you see there is a bubble interactions occurring between them, and this is just a beginning of that. You can do this kind of games. You can play with certain bubble configurations and look the interaction with waves and with the bubbles together. This has a bit more of an application. We thought, okay, if the bubbles are able to block the acoustic waves, let's do an active. We do it actively, and we generated bubbles at certain layers, 1, 2, 3, 4, 5 layers of bubbles, and then we apply a shock wave from below. If you look carefully here, you see how the quality of this bubble pattern. They should be about 260 micrometers apart. Here, these bubbles, and they're all of the same size. I'm really excited now. This looks from the side. The picture is not optimal. It will get better, but here you look from the side. Because of this funny illumination, we see shock waves, but we also see every dirt. So there's a lot of dirt along the optical path. But just this is the hydrophone here on the top. These are the 5 layers of bubbles. And now we let the wave travel through it. This is the pressure wave coming in. Then the tension comes on the back side, and you see all these thousands of waves from these bubbles, which are collapsing along the acoustic path, are emitted. And you see also there's some activity happening within this bubble structure. Now we can look what this effect is. We can look at the acoustic pressure below and above. Let's look first below. This is about 120 bars of positive pressure coming here when we put the hydrophone at that side. And if we put the hydrophone on that side, we get MER of 6 bars here. It's a strong acoustic damping by these few layers of bubbles. Are you all still with me?
Yeah.
Yeah, Stefan, good. How much time do I have?
Yeah, as long as you want.
I have the last thing to tell you, and that was stimulated some time ago in 2012, still in Singapore. Philippe Marmonton, and actually his then I think PhD student. Now he's I hope he's Oliver Vincent. Is he in? I don't know where he is. No, but maybe you know where he is now. They were interested in.
Grenoble.
Excuse me?
In Grenoble.
In Grenoble. Very good. That is the right place for bubbles. Yes. So they asked me to work with them. They came to Singapore, and we were looking at bubbles in hydrogels, similar to gelatine, but much stiffer. They were interested in cavitation activity in trees, and that was a phantom for a wood material. And again, these bubbles were created with a laser. Yeah, so you make bubbles in a gelatine, not in gelatine, hydrogel with a laser, and then you could fill them with liquid. So everything was filled with liquid. So this was outside was the hydrogel, and inside was the liquid water. So this is pure water, outside is hydrogel. And then this was let to dry. So the water was evaporating from the hydrogel, and that put the structure under tension. Sorry. this put the structure under tension, and then there's a moment when the tension in this liquid cavity is so strong that you get nucleation, cavitation nucleation, and these bubbles, they expand then, and this is a very fast event. So we, at that time, we didn't have a camera to look at this event. No, sorry. And but we used a photodiode, and here the photodiode, you see the oscillation. So this is when the bubble appears, it oscillates a little bit, and the frequency here is ways higher than you would expect as a natural frequency of this bubble of that size, more in the few megahertz range, and you would expect much smaller natural frequencies. The reason is, and that was a lot of work by then Philippe Marmotton and Oliver Vincent, to work on a model on the coupling of the solid with the liquid and the bubble, and they could show that the compressibility of the solid and the compressibility of the liquid together play a game here together, and they lead then to this, they affect the bubble oscillation. And by listening to the sound of these bubbles, one can measure the elastic modulus of the solid. We did this not that long ago, actually 2 years, 3 years back. Actually, Julian came from a different perspective, but it connects very nicely here again. We have again an elastic solid, we have liquid, and we have cavitation nucleation. That was part of the PhD work of Julian Rapet, but also with Pedro. And now we are continuing. I show some new results from our lab now, continuing with that work. So if you create a plasma between two glass plates, you can create interesting waves, elastic waves in the solid too, and they can back react on the liquid. And what we do is we have a thin liquid sheet, maybe 5, 10, 15 micrometers thick. This is a liquid sheet, and on top and below you have glass plates. And glass has also an elastic modulus. It's in the something 50 gigapascal range, so much higher than the gelatine, which I showed you, is only the kilopascal range, but still the elasticity is important to consider. And that was actually an example of an experiment, which we were flabbergasted what can happen. So you create a small plasma in the center, so a high pressure region, and then you get a bubble in the center. That's not something what we are very interested in it. You get this big bubble, and that big bubble collapses, but we are much more interested in the beginning. In the beginning, you see a lot of cavitation everywhere around the center, and has a radial symmetry. And here we show you this is a very, very fast event. So within a few microseconds, everything is gone. So actually happens, the whole cavitation event happens between 0 microsecond and 1 microsecond. And that poses us to a challenge, because we want to understand what is going on. How do all these bubbles appear? We are not looking at this center bubble. This is a big cavitation bubble, very well studied. But why all these little bubbles around appear? And here we used a streak camera. And we look now what happens here in a very high resolution, but only in a 1D. Yeah, so along this line, we take a very fast recording. So the line is here, this one, and the recording time is in this direction. So you don't see the 2D picture, but only a streak of it. So initially we get a plasma, and then you see this is the primary bubble. This is the primary expanding bubble in the center. This expands very slowly, but then you get a lot of these black dots, and this is the cavitation structures which you have seen there, and they move out with a very fast velocity initially, and then it drops down below the speed of sound. So and then these bubbles which appear here, they collapse after some time, and some live a bit for longer. But you see only the time region here is 1.5 microsecond. So very fast events happening after the nucleation of these laser plasma in the liquid. And here it was very helpful to use very short exposure times, and then you see in detail what is going on. 18 nanoseconds, really 80 nanoseconds after the laser was shot, you get a structure here outside by short exposure times, you get which is a bulk wave. This is a bulk wave, a longitudinal wave traveling in the solid. And then you get a little bit here this wave is a leaky Rayleigh wave traveling with a speed of something like 3,000 meters per second. And that is a surface wave. And then we also have a propagating wave here, where the bubbles are nucleated, at which is a speed closer to the speed of sound in the liquid. And we were asking ourselves, what is causing this one? And here we did some simulation. What happens if you have an elastic solid with a high elastic modulus? Here you have a liquid where you account for the acoustics, a linear acoustic model. This is a solid model. What happens actually? And we see all these kinds of waves. This is a very fast wave. This is the leaky Rayleigh wave, which travels outwards here and is also losing a lot of its energy. And then something which travels here slowly out, also losing its pressure, but this is much slower. This is a new kind of wave, or not a new kind of wave, but a wave we didn't really expect. And I'll tell you about that wave now. And these pictures, you can see that you have the bulk wave. This is very weakly coupling into the solid. The leaky Rayleigh wave couples into the solid, into the liquid. The bulk wave doesn't couple very much. This is fast, leaky Rayleigh. But this wave, which comes later, is a lamp wave. This is a flexural wave, which you typically have in thin plates. Now, the restoring force doesn't exist in water, but the two solids on above and below do provide a restoring force. And so you have the possibility of a symmetric or anti-symmetric mode. This is like this. If it's symmetric, then you have an expansion. It goes up and down simultaneously, or anti-symmetric, they both move in the same direction. And this can lead to waves traveling in the water. And we did the analysis, what kind of speed you would expect, depending on the elastic modulus, also depending on the thickness. And we see that mostly symmetric waves can propagate in the low frequency range. We are probably around less than 100 megahertz here with this excitation. And then you can also look what kind of displacements you need, a few nanometers you need, that you get in the range of up to kilobar of pressure or tension. And that is the exciting thing. You can create enormous tension in the liquid with these waves. So you will easily reach the homogeneous cavitation threshold, or any threshold, cavitation threshold you can imagine. And this depends more or less only on the initial plasma pressure. And typically plasma pressures are in the range of tens of gigapascal. So you can create with these kind of simple experiments tension in the liquid of the kilobar range. Here's a nice picture from Patricia. She has done that, I think, with a Shimatsu camera. And here you see all these kinds of bubbles. You have this initial bubble here generated, and you have the lamp wave, which nucleates the cavitation bubbles. You have the leaky Rayleigh wave and the bulk wave outside. So the last slides, and I'm done in 2 minutes, is that we have been looking here from the dielectric breakdown. We get a plasma there. You get a primary cavitation bubble, which is interesting for some, but we don't think it's so exciting as this cavitation nucleation in this thin gap. This central bubble is slow, but we get very strong waves in the solid, which lead then to secondary cavitation. And this creates, on a microscopic scale, very strong tension, very predictable, and the tension drops with distance. So you have also a measure of the strength as a function of distance. So we thought, okay, let's test if these are actually very good cavitation. Can you test cavitation nuclei? And the first cavitation nuclei we came to our mind are these very small black dots. You hardly see them. Can you see them, these black dots? These are microbubbles, and because of our resolution, we can't see them with just 1 pixel. These are luminity microbubbles. And if you apply this wave, you see all these bubbles, they expand and nucleate into cavitation bubbles. And then we thought, okay, bubbles are fine, but what happens to oil droplets? So cavitation nuclei are considered either to be gas in stabilized by some shell, or gas stabilized on particles in a hydrophobic crack. That is the common cavitation nuclei model. But what is actually missing is, could also droplets being cavitation nuclei? And oil has a very interesting property. It has a much higher saturation concentration than water. And typically oils have about 20 times higher saturation concentration for nitrogen. So if you put an oil droplet under strong tension, does it also act as a cavitation nuclei? And here we use the special kind of droplet, is PFOB, which is used already as a contrast agent for MRI and for ultrasound, because the speed of sound is much, much smaller than of water. So you see it as a contrast agent, has no spins, is completely fluorine and brome molecules. There's no hydrogen here in that oil. And we use these kinds of oil droplets, which are shelled with a small surfactant, and apply now the pressure wave. I'm not sure if you can see there's some red dots. We have to work a bit on that. The red dots are the positions of the oil droplets. And maybe you can go back here. The oil droplets are these small white dots here. These are oil droplets all over the field. Yes, they are again about 2 microns. And here the cavitation is nucleated. And then if you look carefully, a lot of these oil droplets, which we saw before, are becoming active nucleation sites. And one oil droplet is pretty big to see. This one here, there's a big oil droplet here on the side. And that becomes also that you get a lot of bubble activity along this oil droplet. So that is very exciting. Not only microbubbles or particles can be cavitation nuclei, also oil droplets can become cavitation nuclei. Important to mention is there is no phase change. So these oil droplets remain oil droplets. They don't become a vapor here in that process. So just to motivate that research, we can create tension very locally. You can look at it with microscopic methods. If you have the high-speed cameras, you can look at high speed. So you can control the tension locally very nicely. And you can then look for the effect of cavitation on certain issues. That was one, what are cavitation nuclei? But here's a nice example also that with this cavitation, when you expand this bubble and they collapse, they also remove dirt. This dirt here, what you see, okay, yeah. This dirt, which you see here on the bottom, this is ink. And if you apply cavitation on this surface, you actually clean it, yeah, you at the spots, and can look for this kind of effects. Another way to use these thin gaps in cavitation is looking at sonochemistry. You would now know where where cavitation happens, and can maybe look locally also at chemical reactions, maybe with fluorescence, Raman, whatever you have there in your lab available. So the research was done not by me. Actually, I didn't touch any of these experiments. They were done all by these wonderful people I had the chance to work with. And just to mention, I mentioned the first 3 already, but also Patricia Pfeiffer, she has been working on this cavitation nucleation, continued with the oil and the microbubbles. Saber worked on high-speed imaging with plane waves. He's a PhD student. Siwan Oh is my wife, but besides, she's also working in the lab here on shockwave passage, with the A is missing in bubbly elastic solids, together with Juan Manuel Rosello, who is has also shown these pictures with droplets, bubbles expanding in solids with particles. Fabian Reuter has done these bubble clusters, the wonderful work there, and the little CFD simulation I showed you, but many more he has done is done by Hendrik Riese. So thank you very much for your attention, and if you have questions, I'm happy to answer them directly.
Thank you very much. Well, of course, there's, I guess, some questions. I can start maybe. There's a lot of amazing experiment there. If you go to slide 24, I have just a question there.
24.
24.
Okay, let me go there. This one?
Yeah, exactly this one. It's amazing to observe the waves that you create with the bubble on the surface. So you don't have to use special optics there. It's just white light contrast that we can see here. Or is it polarized?
This is this one.
Oh.
Is this technique? Yeah.
Okay, it's polarized light. Okay. So if we come, this was not my question. My comment, I would say, is that it's amazing. I don't know if you have measured the speed of your waves there, of your shear waves, and the speed of your crack, because in seismology, it's very important to study how earthquake occurs, and sometimes the cracks that are responsible for earthquake propagate faster than shear waves. So it's the super shear regime. And my guess here is that you have a crack that goes faster than the shear waves. So you are exactly in the configuration where you have a super shear regime for your crack. You have to compare the shear wave speed and the speed of the cracks. And here it appears that your crack is bigger than the distance of the shear wave front. So my guess is that you are here in a super shear regime for the cracks, which is rare.
Thank you very much. This is excellent to talk with you guys about that. I'm not so much into solids. We're learning now things like that. So we looked at it first by the bubble. The bubble is moving faster than the speed of the shear waves downwards. So the force with which this high strain region is generated is like stress confinement. Yeah, the bubble moves fast downwards, faster than the wave can travel. This is happening here. So the bubble center, actually, if you look, it moves downwards. It moves here, from here to here. This is faster than shear wave velocity. Here is about 3 meters per second. And the crack, as you rightly say, this also moves faster. This is as a result of that strong tension, downwards force by the bubble moving downwards is following probably this fast motion of the bubble.
Yeah, very interesting. Okay, so do we have questions? Other questions? Online? Yeah, please go ahead.
I have a question. I'm Maxime, but thank you very much for your very interesting talk. So I think it was about. So you have this possibility to generate these bubbles cluster and specific geometry. And so have you ever tried to or thought about using such a geometry as you said as an ultrasound array, like trying to, I don't know, using it to just like an ultrasound array and being able to focus with these bubbles, like oscillating bubbles, on a specific area or
exactly. This is a very good idea, and indeed, I've showed you two things. The first one is that the speed of sound you have seen before, the speed of these shock waves or acoustic waves is a function of the void fraction. Yeah, that was this was the first one. Where was this? Here. So here, there is the speed is a function of the void fraction. Mm-hmm. So if you have a more dense cluster, then you would have a lower speed of sound. And if you have a less dense cluster, you have a higher speed of sound. Now, your idea to use these bubbles as a focusing element or defocusing element could be, we haven't tried it, but could maybe be done by changing the density of these bubbles. So you have a very dense cluster, you have a lower speed of sound. If you have a less dense cluster, you have a higher speed of sound. And that is very similar to a lens or a gradient index lens, and you can make focusing of waves. So indeed, this is something we're working now in the lab. Fabian Reuter is now doing the programming, and then we need to measure with a hydrophone the whole thing. But yes, it goes into the direction of metamaterials or acoustic materials by adding these bubbles in elastic solids.
Okay. Because exciting a part of the bubbles with a certain phase delay and not the others would be difficult, but playing on to be sure I understood, but playing on the density, like the local density of your cluster, would be a help in focusing and getting a constructive interference or not.
It's like a lens where you have the phase velocity. Depends on this, either on the index of refraction or the thickness of the material. By the lens, normal lens, you have the thickness of the material, or in a gradient index lens, you do it by doping the lens with different materials, and you can change the index of refraction locally and focus light.
So you would have a void fraction like that depends on the position in the cluster.
Yes.
Okay.
But this is only an idea. It's not done yet. But exactly, your idea is the same as we had here. Okay. Yes.
Very cool.
Just play with these kind of structures, and it seems not so like here. You see that they're beautifully orientated and very similar size. I think there's a lot to play. Yeah,
sure. Yeah, it reminds me the work of Philippe Marmottan, who is doing this dodecahedron bubbles, but with solid structure.
I love that work. I was so excited to see it. He gave a presentation here in our group, and yes. This was also the first. That's why we do the dodecahedron bubble, because we thought we need a platonic solid for the beginning.
Yeah, sure. And another question I have, I think it's about almost the last slides. I guess 55. I'm not sure, or maybe a bit before. I don't know, but it's before that, but. Maybe it doesn't matter. So your bubble, maybe again before. But your bubble cavitations, here, that's the one. Do not appear randomly around the center. So they actually appear in a few circular shapes.
Yes.
So how is that? Is it because of so the spacing between the circles, the bubble circles, corresponds to the wavelength, or is it because there are several waves? Or I don't know. I'm not sure.
Right. Good, very good point. I have no solution for it. I agree with it. It could be this. It looks like the spacing of these lamp waves. This is the wavelengths of this lamp wave. It's not a single frequency because it's a short exposure. So you have maybe a dominant wavelength which coming in. Plus, it could be, but this is what I'm just guessing. There needs to be more work done. It could be the bubble-bubble interaction. So the bubbles expand very rapidly, and therefore the pressure increases around them and stopping bubbles nearby to expand. So there's a neighborhood where no bubbles can expand, and then at a certain distance again, when the tension is sufficiently strong, you expand the next layer and next layer. Yeah, so, but yes, you immediately see it, but it might be not an easy explanation what causes this ring structure.
Okay. Well, thank you very much.
Welcome.
Yeah. Any other questions? No. The speed of sound in a bubble cloud. We sometimes call that the coffee cup experiment. You are aware of that, Klaus?
Yeah, so I just try to switch on. No, please tell me about the coffee cup experiment.
Well, you take an espresso, and then you, with your spoon, you knock the bottom of your cup, and then you hear a noise. And if you hit several times, you can hear the sound, which is changing because you have a lot of bubbles. And then when it degas slowly, you can hear the change of tone due to the change of speed of sound in the cup. So it's the cup of coffee experiment. Very easy to do every morning.
Yeah. You're reminded by the beautiful bubbles. Yeah, yeah. That is much nicer. I think Ron Roy has done an example or an experiment where he to show the students that the speed of sound changes, but it was much more complicated. Big setup, but this is much more beautiful. Yeah.
No more questions here in the audience? No. No more questions anywhere?
Yeah.
No.
I want to say sorry for my inability to run this Microsoft Teams, but now I know it. Next time I.
Absolutely no problem. Okay. Okay. Sorry. Maybe there is a question. So here. No. Just thank you. Can we have the record of the seminar? I don't know if somebody recorded it. This is a yes. Okay. Yes, it was. So okay. Yeah, we can send of course the video. Yeah.
Sure.
Okay, is there some well, j'entends rien. Okay. All right. I think we don't have no more questions. So thank you again, Klaus, for all these amazing results. It's really beautiful, and maybe
I hope to meet you guys.
Soon. You will come here. And we'll invite you to the restaurant. This is what we do usually in normal times. So hopefully you can come in Lyon whenever you want.
Yes.
Okay.
Very well. Thank you very much. And
thank you very much.
Have a good lunch.
Thank you. You too. Au revoir.
Au revoir.